are standing on a pane of glass. Below you is a 300-meter drop into a misty canyon. Every instinct screams to step back. This is Zhangjiajie National Forest Park. The sandstone pillars here rise sheer and vertical, creating massive drops that dictate the geography of the landscape. When architect Haim Daton was commissioned to bridge one of these immense gaps, he faced a strict mandate: cross to Oid without destroying the park's World Heritage visual environment. Daton drew on the Taoist philosophy of Lao Tzu, who stated that great form is invisible. The goal was to build a structure that would visually dissolve into the mist. The result is the Zhangjiajie Grand Canyon Glass Bridge. Suspended between two cliffs, it appears as a thin, fragile white thread. But the illusion of nothingness is exactly that, an illusion. Making 2,200 tons of steel and glass appear weightless required designing one of the most mechanically complex and dynamically responsive suspension bridges in history. The sheer distance is the first obstacle. The main suspension cables span 430 meters across the canyon, carrying a pedestrian deck that stretches for 385 meters. The structural anomaly lies in its profile. The entire deck is supported by a steel girder measuring exactly 60 centimeters deep. In structural engineering, the relationship between how far a bridge stretches and how thick its supporting deck must be is called the span-to-height ratio. A typical suspension bridge maintains a conservative ratio to ensure rigidity. This bridge pushes that ratio to an extreme 625 to 1. A deck this long and this thin is highly flexible. Without massive bulk to weigh it down and stiffen it, the structure is highly vulnerable to deformation from natural forces. To keep this razor-thin structure intact, engineers had to solve three physical crises: the sheer weight of gravity, catastrophic wind flutter, and human-induced resonance. When we think of a structural glass floor holding 800 people, we imagine thick, monolithic slabs of solid material. The reality relies on the science of composite lamination. Looking closely at the composition of a single 3x4-meter deck panel, we see it as not one piece, but 5 distinct layers. The primary load-bearing material consists of 3 identical 16mm thick layers of ultra-clear, low-iron tempered glass. Sandwiched between these are 2 microscopic layers of Sentry Glass Plus, or SGP, an ionoplast film. During manufacturing, this specific polymer binds with the glass chemically, providing extreme stiffness and toughness that individual glass panes lack. This creates a vital failsafe. If all 3 layers of glass somehow shatter, the SGP film maintains enough structural integrity to hold the intended payload. Engineers demonstrated this visually by striking test panels with sledgehammers. Even completely fractured, the laminate structure holds the load without collapsing. In rigorous testing, a single panel was subjected to 20 tons of centralized weight. The panel deflected a precisely measured 2.16 centimeters. The floor is an engineered structural composite designed to bend predictably under extreme stress rather than break. With the floor materials proven, the macro challenge shifts to suspending those panels securely across the canyon. The entire system hangs from 4 reinforced concrete towers, firmly anchored into the cliffs on either side. This diagram illustrates the spatial cable plane engineers employed to stabilize a 60-centimeter thick deck over this distance. At the towers, the main cables are spaced widely apart, spanning 45 to 50 meters transversely. From there, they angled sharply inward to attach to the deck, which is only 6 meters wide. This severe inward taper provides crucial lateral gravitational stiffness. The geometry physically forces the lightweight deck to remain perfectly centered over the void. Canyons are natural wind tunnels. Topography compresses passing air, accelerating it to extreme velocities with unpredictable angles of attack. During a 6-month program at Hunan University, models of the bridge were blasted in a wind tunnel, with velocities reaching 56 meters per second, over 200 kilometers per hour. For a highly flexible, thin deck, wind introduces the catastrophic threat of aeroelastic flutter, where the structure begins absorbing energy from the wind and oscillating uncontrollably. This cross-section shows what happens when extreme wind hits a standard flat bridge deck. The blunt edges cause the airflow to separate into swirling, alternating pressure pockets. This periodic shedding of wind creates vortex-induced vibration, pulling the structure up and down in a rhythmic, destructive cycle. To prevent this, the 60-centimeter steel girder is shaped as an inverted trapezoid. Along its outer edges, engineers attached sharp, angular steel plates. These plates act as spoilers. They slice through the airflow and disrupt organized vortex patterns before they can induce a dangerous vibration. Stabilizing the girder wasn't enough. The wind tunnel data revealed a conflict with the architect's pure aesthetic vision. The original plan called for completely transparent glass handrails to maximize the illusion of an invisible structure. That design had to be scrapped. Solid glass rails act as a sail, catching the wind. Instead, steel pole handrails were installed. This increases the structure's aerodynamic porosity, allowing air to pass through freely and significantly reducing lift and drag. To survive, the bridge could not fight the wind. It had to become an aerodynamic blade, proving that physics ultimately dictates architectural form. Securing the bridge against nature solves only half the dynamic equation. The other threat is the payload itself, up to 800 moving pedestrians. Suspension footbridges utilizing lightweight steel and glass floors possess remarkably low natural frequencies. If the rhythm of a crowd walking aligns with the natural frequency of the bridge, it triggers resonance. The structure begins amplifying the footfalls into a self-feeding loop of mechanical energy. This precise phenomenon forced the closure of the London Millennium Bridge in 2000, when synchronous footfalls caused violent lateral swaying. This X-ray view reveals that the solution to this resonance is hidden entirely within the hollow spaces of the 60-centimeter deck. The first line of defense is a series of tuned mass dampers. Distributed along the span are 50 500-kilogram glass balls. Their physical inertia actively absorbs the vertical bounce generated by pedestrian traffic. System 2 utilizes tuned liquid dampers. Large water reservoirs are built directly into the structure. As the deck sways in one direction, the mass of the water sloshes out of phase in the opposite direction, deadening the movement. The final safeguard is a network of eddy current dampers. These electromagnetic devices provide high fatigue life vibration control. They use magnetic resistance to turn the kinetic energy of structural movement into dissipated heat. This seemingly fragile, invisible bridge contains a dense, hyperactive mechanical nervous system that is constantly fighting the crowd's momentum to keep the deck perfectly still. Looking at the finished structure in operation, crowds walk calmly across the clear glass, suspended over the drop. The water tanks, the electromagnetic dampers, the aggressive steel geometry, all perfectly concealed within a profile measuring just 60 centimeters. This strict concealment achieves the architect's goal of a structure that harmonizes with the surrounding cliffs, enforcing the Taoist principle of minimal visual impact. The terrifying feeling of stepping out over the void remains entirely intact, precisely because the massive machinery keeping you alive is out of sight. But the crossing is not an act of faith. It is an act of applied physics. Every degree of transparency and thinness is paid for by rigorous mathematical compromise and advanced material engineering. The hesitation a person feels stepping onto that glass is deeply human, but the fact that the glass holds firm is a triumph of uncompromising engineering. The Jinsha River Gorge is an exceptionally hostile environment. Long before a single drop of concrete could be poured, engineers had to figure out how to anchor a structure into these steep, highly unstable walls. Any dam built here has to safely hold back a 289-meter wall of water. That massive reservoir exerts 16.5 million tons of constant physical thrust against the surrounding rock that is already prone to violent landslides. The geography itself is severely lopsided. The left bank of this canyon stretches out 101 meters longer than the right. The rock making up these cliffs is called columnar jointed basalt. It's a fragile geological formation of interlocking hexagonal columns. The moment you excavate it and change the pressure, these basalt columns violently relax and fracture. Building a megadam in this location requires fighting a mountain that rejects being tamed at every structural level. A traditional symmetrical arch dam placed into this lopsided gap would shatter under the uneven stress. To survive the geography, engineers utilized the equilibrium design method. Instead of centering the structure, they mathematically manipulated the geometry of the dam itself. They shifted its center line 20 meters toward the left bank and rotated the entire footprint exactly 5 degrees. This exact asymmetrical alignment ensures that the 16.5 million tons of water thrust pushes evenly into both the long and short riverbanks, perfectly balancing the load. The result is a massive double-curvature arch dam locked flawlessly into a chaotic gorge. The structure achieves absolute stability because the concrete was forced to adapt to the mountain's geographical flaws, rather than trying to force the rock to adapt to the concrete. Pouring 8 million cubic meters of concrete introduces a massive chemical hazard. As concrete cures, it generates extreme heat. If that heat builds up too fast, the material expands and cracks under its own thermal stress. To prevent this, the builders mandated the exclusive use of low-heat Portland cement, or PLH, across the entire structure. By altering the chemical makeup, PLH significantly lowers the heat of hydration during the curing process. This chart tracks the thermal output of concrete over a 28-day curing cycle. You can see the sharp, dangerous heat spike generated by traditional cement on the left, compared to the low, highly controlled thermal curve of the PLH cement on the right. To reinforce this chemical defense, thousands of internal sensors and water cooling pipes were embedded directly into the blocks, constantly reacting to keep the core temperature strictly between 21 and 27 degrees Celsius. Because of these tightly controlled thermal limits, this 300-meter class megastructure was completed without a single temperature-induced crack. The civil engineering above ground is matched by the heavy electromechanical excavation below. Deep inside the canyon walls sits a cavernous network of generator halls. These halls house the 1-gigawatt Francis turbine. Operating at 1,000 megawatts each, these are the most powerful hydroelectric machines ever constructed. A single complete unit stands 50 meters tall and weighs 8,000 tons. Spinning that much mass requires microscopic precision. The central rotor alone weighs 2,000 tons, but operates with a maximum swing tolerance of barely 0.05 millimeters, about the width of a human hair. At this scale, generating electricity creates immense heat. Safely insulating 24 kilovolts of power requires advanced, fully air-cooled systems to prevent the massive units from melting down under their own electrical load. By combining the physical scale of a skyscraper with the mechanical precision of a wristwatch, these generators convert water into electricity with a 96.97% efficiency rate. The final logistical hurdle is geography. Baihetan captures 16 gigawatts of power deep inside an isolated mountain range, but the heavy energy demand sits thousands of kilometers away on the eastern coast. To move that power, engineers rely on plus or minus 800 kilovolt UHVDC, or ultra-high voltage direct current transmission lines. These specialized lines act as a 2,000-kilometer energy artery. They use hybrid cascaded technology to regulate the voltage, actively stabilizing the regional power grid as the electricity arrives. This power flows directly into the massive coastal economies and brightly lit megacities of Jiangsu and Zhangzhou. Looking at a map of China's river systems, Baihetan is the final piece of a 6-dam clean energy corridor. As this cascade of dams sends a continuous flow of renewable energy eastward, it offsets millions of tons of coal emissions every year. Mastering extreme physical limitations, from microscopic rock fractures to the vast distances of a continental power grid, allows us to safely harness the ultimate scale of nature. At 632 meters tall, the Shanghai Tower commands the skyline. It pierces the clouds and interacts directly with high-altitude weather systems. Building a structure of this weight on the clay-based soil of a river delta is a massive undertaking. To complicate things further, this coastal location sits directly in the path of typhoon-force winds. This landscape was transformed in 3 distinct architectural stages. The first was the Qinghai Tower, completed in 1999. Its tiered, stepped design is a direct nod to the pagoda-style architecture of China's past. Next came the Shanghai World Financial Center. With its sharp edges and the rigid, trapezoidal aperture at its crown, it reflects the unyielding economic expansion of the present. The Shanghai Tower serves as the final component of the trio, a structure built to test a new, sustainable model for high-density urbanism. Reaching well over 2,000 feet required moving past traditional rectangular footprints. To keep the building standing, engineers had to develop an entirely different geometry. Vortex shedding is the primary concern for a building at this scale. When high-altitude winds hit a flat surface, the air splits and creates alternating, low-pressure, swirling vortexes on the sides. This creates a constant tugging motion that causes the tower to sway. To find a shape that could disrupt those vortexes, the design team tested over a dozen different models in a special tunnel. The resulting solution was this cam-shaped equilateral triangle profile. As it rises from the ground, the entire building spirals exactly 120 degrees. This specific twist achieved a 24% reduction in wind loads. Neutralizing those forces meant the structure required 20,000 fewer metric tons of steel, which saved $58 million in material costs. The tower's twisting silhouette isn't an aesthetic choice. For a building of this height, this specific shape is a requirement for survival. Holding up that complex form requires a specialized internal skeleton. This 3D diagram shows the tower's central concrete core interacting with a perimeter system of diagonal supercolumns. To maintain stability, engineers utilized massive outrigger trusses. These act like ski poles, extending horizontally from the inner core to the outer supercolumns to lock the entire frame together against the wind. While the skeleton provides strength, engineers use this 1,000-ton tuned mass damper to manage the remaining sway. It is suspended within the building's crown to maintain comfort on the upper floors. Unlike traditional dampers that use hydraulic oil, this system utilizes magnetic drag. As the building moves, an array of magnets swings over a copper plate, creating a frictionless eddy current that smoothly counteracts the tower's motion. That same stable core houses Mitsubishi elevators that travel at 20.5 meters per second. As they descend, they utilize regenerative power to offset the building's total energy consumption. By combining a reinforced internal frame with a magnetic damper, the building successfully turns high-altitude wind forces into a stabilized internal environment. This cutaway model shows the tower's double-skin facade. The building consists of two independent glass envelopes separated by a massive void. This allows the tower to function as 9 distinct vertical zones, cylindrical neighborhoods stacked on top of one another. The space between the two glass skins houses 14-story-tall sky gardens. These atriums are filled with trees and public seating, providing natural light and open air thousands of feet above the city. These gardens are a modernized version of traditional Chinese shikumen and hutongs. They take the communal courtyards usually found in ground-level alleyways and bring them directly into the tower. The double skin also functions as a giant thermos. This diagram shows how the atrium space buffers outside temperatures, which reduces the energy needed to heat and cool the interior offices by roughly half. This thermal buffering is part of a larger ecosystem that earned the tower a LEED Platinum rating. The building recycles rainwater for its internal systems, while the crown houses 270 wind turbines to generate its own renewable electricity. By integrating a twisted aerodynamic form with communal sky gardens and magnetic engineering, the Shanghai Tower provides a different template for how high-density cities can function. The Songhua River wetlands in northeastern China are a place of survival. During the winter, temperatures on the floodplain drop to -40 degrees Celsius as winds strip across the frozen water. This is Harbin, the ice city. For its 5 million residents, winter is defined by navigating heavy snow, slushy streets, and sub-zero reality. Historically, Harbin's architecture has followed a rigid industrial logic. The city is a network of repetitive grids and apartment towers that remain physically and emotionally disconnected from the surrounding landscape. When local planners set out to build a cultural center on 444 acres of raw wetland, they realized that a standard glass and steel box would be lost in the vastness of the marsh, failing to anchor the site or provide a sense of local identity. A successful landmark had to function as a physical extension of the terrain, growing out of the snow and ice rather than merely sitting on top of it. To solve this, the city turned to architect Ma Yansong and his firm, Mad Architects. Ma guides his practice through a philosophy called Shan Sui City. He aims to restore the spiritual connection between urban residents and nature by using the mountain and water motifs found in traditional Chinese landscape paintings. The Harbin Opera House is the three-dimensional translation of that vision. It is a structure that turns the harsh conditions of the northern wilderness into a fluid sculptural topography. A massive steel skeleton supports the building's undulating forms, all wrapped in a skin of smooth white aluminum panels that mimic the surrounding snowdrifts. Creating these organic curves required a solution to a massive thermal problem. The building's exterior must survive an annual temperature swing of 80 degrees Celsius. As temperatures fluctuate, these massive aluminum panels expand and contract, creating significant linear movement across the facade. To fill the gaps, engineers used specialized Sikasil sealants. These joints absorb up to 10 millimeters of expansion, remaining completely watertight and windproof in sub-zero weather. This engineering allows the entire shell to move in sync with the climate, shifting safely through the region's extreme seasonal cycles. The architecture invites the public to climb its roof like a mountain path. A granite stairway snakes up the white aluminum curves, leading to an observation deck 35 meters above the marsh. Above the lobby, the roof gives way to a crystalline glass canopy made of hundreds of transparent pyramids. Customized to handle the ice city's heavy snowfall, heat sensors trigger a snow melting system that directs runoff into integrated drains hidden beneath the facade. By keeping the glass clear of ice, natural light can always reach the spaces below. The design treats the environment as a resource, flooding the lobby with daylight even during the bleakest winter months. Transitioning from the stark marble lobby, visitors enter the Grand Theater, a space that feels like a warm, sheltered sanctuary. The 1,600-seat theater is encased in a shell of undulating Manchurian ash. This sound model reveals how the eroded shape of the timber walls functions. The organic ribbing reflects sound waves to every seat, providing world-class acoustics for both Western opera and traditional Chinese performances. The material and its horseshoe shape were chosen to emulate the warm, resonating interior of a musical instrument. The smaller 400-seat theater takes a different approach. Behind the stage, a massive panoramic window made of soundproof glass looks directly out into the marshlands. This window turns the exterior wilderness into a living backdrop, visually connecting the performance inside to the landscape outside. At night, the building glows like a beacon on the Songhua River, creating an emotional anchor for the public in an otherwise desolate environment. The 1.4 billion RMB price tag transformed a remote wetland into a public topography, replacing the cold efficiency of the industrial city with an accessible spiritual landmark. It is a physical argument that the future of the city doesn't have to be a battle against the natural world. The Shan Shui philosophy provides a way to integrate human activity with the environment, prioritizing the spirit of a place over rigid engineering. The Harbin Opera House functions as a cultural center where the wilderness is no longer just a backdrop. It is the very essence of the architecture itself. Connecting Hong Kong, Zhuhai, and Macau requires spanning 55 kilometers of the Lingdingyang waters. Building a structure across this exact geography presents a severe spatial conflict. The central Lingding Channel is a primary marine artery. It requires deep draft vertical clearance to accommodate 300,000-ton oil tankers passing through the estuary. This 3D topographical model maps the airspace required for that shipping lane as a vertical volume. Any physical bridge deck must sit above this column. However, the immediate proximity to Hong Kong International Airport enforces a strict aviation ceiling. A descending cone of radar and flight path clearance presses down from above. The mathematical intersection of the shipping column and the aviation cone creates a strict no-build zone. The required deck height to clear the ships exceeds the maximum tower height allowed for the planes. A continuous traditional suspension bridge cannot exist here. The structural constraints extend below the water. The baseline geotechnical profile of the estuary features a 30-meter thick layer of highly unstable, soft seabed soil. Above the surface, the region sits within severe typhoon corridors, demanding high aerodynamic stability and extreme lateral load tolerances from any exposed architecture. Furthermore, these waters serve as the protected habitat for the endangered Chinese white dolphin. Heavy industrial disruption to the marine ecology had to be minimized. These combined forces, the spatial conflict, the soft seabed, typhoons, and ecological protection, ruled out a standard linear bridge. The solution required a multimodal hybrid infrastructure system. In the shallower channels outside the flight path intersection, engineers designed 3 distinct cable-stayed spans, the Qingxing, Shanghai, and Zhuzhou bridges. Each is calibrated to stay below the local aviation ceilings. The steel towers rely on specialized structural geometry, such as this Chinese knot design, to anchor the cable stays while managing wind shear. Constructing these elements in the open ocean through traditional concrete pouring carried extreme weather risks. The strategy shifted to factorization, massive off-site prefabrication. Bridge piers were cast in controlled inland facilities, carefully transported by specialized marine cranes and precisely aligned in the water. This logistical chain culminated in hoisting 2,600-ton steel bridge towers and locking them into place as single completed pieces. By moving the manufacturing off-site, the engineering teams mitigated marine weather delays and achieved millimeter-level alignment accuracy at an oceanic scale. To bypass the central no-build zone, the roadway must submerge. This required 2 100,000-square-meter artificial islands to serve as transition points. Traditional island building relies on dredging the soft seabed. Doing so here would displace millions of cubic meters of suspended particles, devastating the dolphin habitat. This schematic illustrates the large-diameter, deep-inserted steel cylinder method. Open-ended steel cylinders are driven through the soft soil into the stable foundation. Arc-shaped steel plates interlock adjacent cylinders, creating a highly stable, watertight cofferdam wall that encloses the island perimeter without excavating the seabed. Inside this sealed ring, sand and structural fill form the physical transition island and the portal to the undersea route. This non-dredge method reduced suspended particle pollution by 70%. 33 distinct concrete tunnel elements were floated into the channel, systematically sunk and locked together along a prepared trench. At 40 meters deep, the structure uses a semi-rigid joint design. These joints flex to absorb seismic activity while maintaining a hydrostatic seal. Once positioned, 23 meters of backfill are layered over the roof, pressing down to stabilize the elements. Only an immersed tube architecture possesses the load-bearing capacity and horizontal flexibility required to survive this exact geological depth. Beyond the natural constraints, the bridge solves a macro-political disparity. Traffic in Hong Kong drives on the left, while traffic in mainland China drives on the right. This top-down schematic tracks the structural solution built into the Hong Kong Link Road viaducts to reconcile the two systems. Across a 1-kilometer span, the physical carriageways are engineered to swap. The tracks curve over and under each other, exchanging left and right orientations. Targeted physical architecture seamlessly resolves the jurisdictional conflict without introducing intersections, stoplights, or bottlenecks. Once built, the structure faces continuous deterioration. High salinity, high humidity subtropical marine environments aggressively corrode reinforced concrete and steel. To meet a strict 120-year design life mandate, engineers embedded a multi-level durability strategy into the physical foundation. The bridge relies on a structural health monitoring system. A continuous network of sensors measures wind stress, seismic tremors, and internal material corrosion. Autonomous robotics systematically traverse the vast structural elements, mapping the physical data and inspecting heavy steel infrastructure for microfractures. Modern megaprojects no longer rely entirely on passive material strength. They require active, real-time durability management to survive. The construction of the Hong Kong-Zhuhai-Macao Bridge required an uncompromising reliance on geometric integration, strict component standardization, and massive prefabrication. The completed 55-kilometer structure is the physical answer to a strict set of spatial, meteorological, and ecological equations. The extreme geographical constraints of the Pearl River estuary forced the design. In solving them, engineers established a definitive global benchmark for hybrid maritime architecture. Look at the skylines that defined the end of the 20th century. They are forests of extruded rectangles. The traditional vertical skyscraper had become a repetitive, two-dimensional habit. Stacking floor plates straight up creates an invisible problem. It physically isolates the people inside. Departments become trapped in their own vertical silos, cut off from the rest of the organization. In 2002, China Central Television, or CCTV, faced exactly this problem, but on an industrial scale. They needed a new headquarters in Beijing to house 10,000 employees. Their mandate was daunting. Take an entire sprawling media empire, from administrative executives to breaking news desks, massive broadcasting suites, and cavernous production studios, and consolidate them into a single site in the central business district. Cramming this many diverse, interconnected departments into a standard vertical tower would suffocate the media process. The architects responded by creating a new architectural species, a three-dimensional loop that forces the entire organization into a single flow of activities. The winning architects were Rem Koolhaas and Ole Sheeran of the Office for Metropolitan Architecture, or OMA. They flatly refused to submit a design for a conventional campus or another towering glass rectangle. Instead, they proposed a three-dimensional cranked loop, a continuous, gravity-defying circuit that looks more like a Z folded in on itself than a traditional high-rise. The sheer dimensions of the proposal were staggering. The structure would rise 234 meters into the air, enclosing a massive 473,000 square meters of floor space. Structurally, it consists of two massive L-shaped towers. They lean aggressively toward one another at 6-degree angles in distinct directions, finally interlocking at both the foundation and the apex. This disorienting geometry forces the viewer to actively engage with the structure. Looming over the central business district, its silhouette changes completely depending on where you stand. It actively resists giving the city a single, easily digestible image. The transition from a theoretical loop to a physical structure requires neutralizing the forces trying to tear the steel apart. At the base, Arab engineers encountered Beijing's shallow, waterlogged subsoil, a foundation incapable of supporting such massive leaning weight. To keep the towers from toppling, the team anchored the building on a 7-meter-thick piled raft foundation. Beneath that raft, 1,242 piles drive up to 52 meters deep, counteracting the immense overturning moments. Above ground, the threat profile was even more hostile. Beijing sits in a high-intensity seismic zone, meaning this aggressive, off-balance geometry also had to survive a major earthquake. A conventional skyscraper relies on a stiff internal core to stay upright. But because the centers of gravity for these leaning towers fall outside their footprints, an internal core would snap. The engineers moved the primary structural support entirely to the exterior skin. They wrapped the entire facade in a diagrid, a diagonal grid. This web of crossing steel beams turns the outer skin into one continuous hollow tube, engaging the entire perimeter to resist bending forces. On this seismic force map, the pattern isn't uniform. Where mechanical stress is highest, the grid is tightly packed. In areas needing less support, the triangles open up. This erratic diamond pattern isn't decoration, it's the building's literal survival mechanism drawn onto its skin. The ultimate test of this system arrived when the two leaning towers finally had to be joined 36 stories in the air. The connection is a 13-story overhang section that cantilevers 75 meters horizontally, suspended over nothing but empty air. To close the loop, steelworkers had to navigate the invisible threat of thermodynamics. Sun exposure heats the steel, causing it to expand. If the final joint was bolted while the towers were at different temperatures, it would lock a permanent thermal stress into the frame, a hidden tension that could rip the joint apart. The timing had to be perfect. The final connections were carefully forged at exactly dawn on December 26, 2007, capitalizing on the narrow window when the winter steel in both towers had cooled to a perfectly uniform temperature. By mastering gravity, extreme angles, and thermal expansion, the engineers successfully transformed a radical architectural theory into an unbreakable physical circuit. The brutalist engineering of the steel loop exists solely to serve the human circuit inside it. With the structure complete, the entire life cycle of television production now flows through the volume of the building along a single path. Oleme designed the loop to act as a social condenser. By bending the floor plates into a continuous circuit, the layout forces formerly isolated departments to cross paths, turning a passive hallway into an engine for interaction. Inside the dramatic upper overhang, the administrative executives sit directly in the primary circulation path. This ensures that every worker, from the director to the technician, shares the same route through the building, physically ending the isolation typical of traditional executive suites. The architecture prioritizes the movement of people and data over the repetition of floor plans. This functional media machine acts as a symbol of collectivism, providing a visible landmark for China's expanding state broadcaster. By linking two leaning towers into a single structural circuit, the CCTV Headquarters demonstrates that high-rise design can move horizontally. It replaces the isolated vertical tower with an interconnected loop, proving that a skyscraper can function as urban infrastructure rather than a detached object. The universe is speaking. Ancient pulsars spin, galaxies drift, and the leftover radiation of the early cosmos echoes through the vacuum. But by the time these radio waves reach Earth, they are incredibly faint whispers. To hear a whisper, you need a large ear. In radio astronomy, this relationship is defined by the radiometer equation. If you want to detect fainter signals, you have to increase your telescope's collecting area. But that creates a severe physical limit. If you try to build a traditional, steerable metal dish that is half a kilometer wide, the immense forces of gravity and wind will literally tear the steel apart. To achieve the sensitivity required for these signals, engineers had to move beyond the physical limits of movable telescopes and commit to an entirely different structural paradigm. The easiest way to solve the gravity problem is to stop fighting it. Decades ago, the Arecibo Observatory pioneered this approach by building a massive, fixed spherical dish directly into the ground. But a fixed sphere introduces a geometric flaw called spherical aberration. Radio waves drop into a perfect sphere and scatter into a messy cluster. Previous designs corrected this by hanging heavy secondary mirrors above the dish, but this weight restricted the telescope's sky coverage. In 1994, Chinese astronomer Nan Rendong proposed an audacious alternative, Tianyan, or the sky eye. He envisioned a 500-meter telescope that would bypass this geometric flaw without the heavy secondary reflectors. It would take 22 years of development to translate that vision into reality, requiring engineers to solve three seemingly impossible challenges. First, the massive scale. Second, the active surface. And third, the flying focus. The first challenge was finding a cradle large enough to hold a half-kilometer instrument. But after evaluating over 1,000 locations, surveyors settled on the Daowodang Depression in the mountains of Quezal. This topographic map shows exactly why this specific karst sinkhole was chosen. Its natural contours closely match the required 300-meter radius of the telescope sphere. The site offered crucial secondary benefits. The highly porous limestone acts as a natural drain, preventing the giant basin from flooding during subtropical storms. Meanwhile, the surrounding jagged peaks form a physical shield, blocking out terrestrial radio frequency interference. By co-opting the Earth's natural geology, the team avoided massive excavation costs while securing a structurally stable, perfectly quiet cradle for a hypersensitive instrument. The second challenge was fixing spherical aberration. Instead of a static metal bowl, engineers built an active reflector composed of 4,450 aluminum panels. Hidden beneath these panels is a massive geometric net of custom-invented steel cables. Because the dish needs to move continuously, these cables were engineered with a fatigue resistance of 500 megapascals, nearly double that of standard commercial steel. 2,225 actuators anchor the net. To track a target, they pull down the cables, deforming the sphere into a 300-meter parabola. Incoming radio waves bounce off this new surface, converging flawlessly at a single focal point. This shape-shifting capability turns a static geological basin into an agile, tracking robotic eye. The final challenge was putting a receiver exactly at that mid-air focal point, without using 10,000 tons of steel to hold it in place. This schematic illustrates the solution: a 30-ton feed cabin suspended 140 meters above the dish. Tracking uses a two-tier system. Tower winches adjust 6 dynamic cables for course positioning, while an internal robotic hexapod makes millimeter-precise adjustments to stay exactly on target. Stripping away the heavy, rigid platforms of the past gives the cabin massive freedom of movement. It can swing widely enough to view the sky at a 40-degree zenith angle, doubling the observable coverage of previous fixed megatelescopes. By stripping away thousands of tons of dead weight, the system covers twice the sky area of its predecessors, expanding the volume of the universe within its reach. Since achieving first light in 2016, the 500-meter Aperture Spherical Radio Telescope, or FAST, has discovered over 1,100 new pulsars, monitored repeating fast radio bursts, and redefined our map of the radio universe. Chief scientist Nan Rendong lived just long enough to see his 22-year masterpiece completed before passing away in 2017. Today, the facility he envisioned is open to the global astronomical community. The telescope stands as a union of natural geology and precision engineering, a massive machine capable of capturing signals from 10 billion light-years away. Anchoring the new central axis of Guangzhou, the Canton Tower stands as a 600-meter marker directly opposite the high-rise commercial district of Zhujiang New Town. Situated where the new central axis meets the Pearl River, the tower's location serves as a pivot point between the city's historical port infrastructure and a modern master plan containing over 70 hectares of new parkland. For most of the 20th century, super-tall structures followed a consistent geometric template, what architects often describe as a masculine typology. These traditional skyscrapers utilize rigid, angular geometries, relying on heavy outriggers and repetitive framing to achieve both stability and height. The Dutch architects at Information-Based Architecture chose a different path, proposing a silhouette defined by fluid, organic curves. This form earned the tower the local nickname Xiaomanyao, or slim waist. Reaching 600 meters with this geometry meant moving away from rectilinear framing. It required resurrecting a 19th-century geometric principle and scaling it using modern parametric engineering. By deconstructing the structure from its foundation piles to its antenna, we can see how the designers used perfectly straight members to generate these complex curves. When architectural form moves away from volumetric stacking toward a tightening silhouette, the structural engineering must transition from standard framing to a logic driven by variable parametric nodes. The tower's geometry is defined by 2 parameters, an ellipse at the foundation and a second 450 meters above. The top ellipse rotates exactly 45 degrees relative to the base. This rotation pulls the vertical lines inward, forming a waist where material is most dense. This creates a hyperboloid of one sheet, a surface characterized by negative Gaussian curvature, where the structure curves in 2 opposing directions. This is a ruled surface. While the finished tower appears rounded and complex, the entire exterior is generated by these perfectly straight lines. This geometric strategy scales the principles of Russian engineer Vladimir Shukov, who used hyperboloid steel lattices to distribute loads equally across a tower surface. This configuration is inherently resistant to buckling because the individual elements remain straight, managing compressive forces. This open lattice also serves an aerodynamic function. Its high porosity allows wind to pass through the structure rather than pushing against solid faces. The 45-degree twist functions as the tower's primary structural logic, aligning the straight steel members to resist buckling while maintaining the slenderness of the waist. Support for the 600-meter structure begins 40 meters underground. 24 concrete piles, each nearly 4 meters in diameter, are driven deep into the bedrock. Above ground, the building utilizes a tube-in-tube system to manage lateral loads from wind and earthquakes. The inner tube is a reinforced concrete core. This solid ellipse supports the gravity loads and houses the vertical transport shafts for the tower's high-speed elevators. The inner core is shifted off-center within the outer lattice. This allows the lattice to taper to its narrowest point without obstructing elevators, and provides a direct vertical path to align the 150-meter antenna mast with the city's central axis. The outer tube consists of 24 conical steel columns. These are bound by 46 horizontal rings and a network of diagonal bracing. Because of the 45-degree rotation, the geometry of every structural intersection changes as the building rises. This required the fabrication of 3,300 unique steel components. Each node and bracing piece was individually designed and connected using universal joints. This parametric engineering moves construction away from repetitive components toward a system of total customization, where every piece is unique to its position in the grid. Beyond its own weight, the tower must withstand the high-velocity winds common to the Pearl River Delta's typhoon season. With a slenderness ratio of 10:1, the structure is highly susceptible to dynamic sway, which can lead to fatigue in the steel and discomfort for guests on the upper floors. This height map shows the placement of the tower's primary defense system. Located at 438 meters on the 85th floor is the hybrid mass damper. Traditional dampening requires adding a massive weight to the top of the tower, but adding unnecessary mass to a gravity-sensitive structure is inefficient. The engineers solved this by repurposing the 1,200 tons of water required for the building's fire suppression system to act as the dampening mass. This water is divided into two 600-ton tanks. These function as a passive tuned mass damper to counter the tower's primary axis of movement. These tanks sit on bidirectional sliding bearings, moving in opposition to the tower's sway to absorb kinetic energy. Mounted on top is a 50-ton active mass damper. Driven by linear induction motors, this active component provides real-time, precise corrections for secondary forces. This creates a fail-safe system. If a power failure occurs during a typhoon, the active motors disengage, but the 1,200 tons of water continue to mechanically stabilize the tower. Structural efficiency is achieved here by merging two separate infrastructure requirements, fire safety and wind dampening, into a single mechanical solution. By distributing the primary loads to the eccentric core and the outer lattice, the architects were able to redefine the interior spaces. The result is a series of column-free megaspaces and open gardens that remain visually connected to the city through the hollow lattice. The skywalk, an open-air staircase, allows visitors to traverse 180 meters of the tower's waist, providing a physical perspective of the geometric twist. To enclose these spaces, every triangular panel of high-strength glass had to be uniquely cut to fit the specific curvature of the ruled surface. This physical structure is monitored by an invisible data network. Over 800 sensors are embedded into the lattice and core to track physical strain, temperature, and acceleration. This structural health monitoring system captures real-time telemetry, transmitting the data down to a central database. While it provides immediate safety alerts, the system also records how the structure responds to rare seismic events and typhoon-level winds. This makes the Canton Tower a 600-meter living laboratory, generating the data necessary to refine the engineering of future super-tall structures. At night, the tower's lighting system highlights the complexity of the lattice nodes. Integrated directly into the nodes and controlled via DMX, these LEDs consume just 15% of the power typically allowed for a facade of this scale. By implementing this non-symmetrical, fluid profile, the tower provided an alternative to the rigid, volumetric forms that dominated late 20th century skyscraper design. It achieved this by scaling 19th century hyperboloid principles into a tube-in-tube system managed by parametric engineering. The Canton Tower demonstrates how extreme-scale infrastructure can move past rigid symmetry to remain graceful, dynamic, and focused on the human experience of the city. On August 8, 2008, 91,000 people gathered inside this illuminated lattice for the opening of the 29th Olympiad. The Beijing National Stadium, or Guojia Tiyucheng, serves as the anchor for a 1,135-hectare urban master plan designed by Sasaki Associates. The stadium occupies a 5-kilometer northern extension of Beijing's historic north-south axis, a line that runs directly from the Forbidden City to the Olympic Green. This placement follows a cosmological layout based on ancient Chinese philosophy, where specific geometric forms are used to balance natural forces. The layout creates a dialogue between the two primary venues, the square water cube representing Earth and the circular National Stadium representing Heaven. During its construction, the public began to refer to the stadium as the Niao Chao, or bird's nest, because of its organic, interwoven appearance. While the aesthetic appears randomized, the steel lattice is the result of precise parametric engineering designed to handle immense physical loads. Analyzing the structure requires looking at how the design team merged the structural frame, the exterior facade, and the roof into a single, unified assembly. The primary architectural vision for the project came from the Swiss firm Herzog & de Meuron. Realizing the complex frame required a collaboration with Arab Sport and the China Architecture Design and Research Group, led by Chief Architect Li Xingang. Artistic consultant Ai Weiwei helped shape the organic aesthetic, drawing on the crackle glaze patterns found in traditional Chinese ceramics. Most modern stadiums utilize a decorative curtain wall to hide their heavy support structures and mechanical systems from public view. The design team for the bird's nest rejected this traditional hierarchy, forcing the raw structural elements to serve as the building's sole visual identity. In clear daylight, the scale of the material used in the exterior shell is fully visible. The structure utilizes 42,000 tons of steel, formed into a massive, intersecting three-dimensional grid. We can digitally deconstruct this grid to reveal the strict load-bearing logic of the assembly. The foundational spine of the stadium consists of 24 main trussed columns that encase the inner seating bowl. Each of these primary columns weighs 1,000 tons. Secondary structural bands intersect these columns, bridging the gaps and establishing the elliptical shape of the bowl. Tertiary steel members fill the remaining spaces, completing the dense visual web and the nest appearance. Vertical loads from the 313-meter roof span are forced downward through this specific crisscrossing path, directly to the foundation. This same asymmetrical web is mathematically calculated to resist lateral wind forces by dissipating them throughout the entire lattice. There are no redundant or purely decorative steel pieces on the building. Every visible member is carrying a load. The gaps between these structural beams are as functional as the steel itself. Planners had to protect 91,000 spectators from the elements without adding solid exterior walls that would disrupt the lattice. They filled the gaps with translucent ETFE and PTFE polymer membranes stretched tightly between the steel members. These membranes repel rain while allowing natural sunlight to reach the inner turf. Acoustically, the membrane serves as a phono-absorbent barrier, reflecting crowd noise back into the stands to increase the energy within the bowl. This open lattice allows for passive natural ventilation, making the building a permeable extension of the surrounding park. By omitting traditional walls, the stadium reduces its reliance on mechanical cooling systems, even during high-capacity events. Beijing's location in a seismically active zone presented the most significant engineering threat to the project. The stadium is required to survive a magnitude 8 earthquake without structural collapse. To meet this requirement, the bird's nest was constructed as two entirely separate buildings. The outer flexible steel lattice is a completely independent system from the rigid red reinforced concrete seating bowl inside. A 50-foot gap physically separates these two structures, ensuring they are not rigidly connected. Steel and concrete have different masses and stiffnesses, meaning they respond to seismic waves at different frequencies. If the concrete bowl and steel roof were a single rigid unit, these differing oscillation speeds would tear the structure apart during an earthquake. Decoupling the structures allows them to sway at their own rates, preventing them from colliding or transferring destructive forces to one another. This 50-foot void prevents a catastrophic collision, allowing the two massive components to move without destroying the building. Constructing a 42,000-ton lattice with almost no straight vertical lines was an immense logistical undertaking. During assembly, the steel could not support its own weight, requiring a forest of temporary support towers to hold the beams in place. Crews welded 128 closure interfaces to transform thousands of individual beams into a single self-supporting shell. The most critical phase involved the synchronized removal of the temporary support towers. As the temporary supports were removed, the entire 42,000-ton structure settled exactly 27 centimeters downward to reach its final stability. The massive building reached its full geometric strength only at the moment it was forced to carry its own weight. Olympic venues often become abandoned white elephants once the games conclude and the global audience leaves. To ensure long-term utility, planners reduced the seating capacity from 91,000 to a permanent 80,000 to better serve post-Olympic events. The stadium's design allows it to function as a gateway to the 680-hectare forest park, fulfilling the 100-year vision of the original urban master plan. The venue's adaptability was proven in 2022 when it was repurposed for the Winter Olympics. It is now the only stadium in history to have hosted the opening and closing ceremonies for both the Summer and Winter Games. The bird's nest remains a functional part of Beijing's fabric, where ancient cosmological geometry and modern parametric engineering serve a lasting urban purpose. Look at the Min River in China's Sichuan province. For most of its path, it is a volatile, high-energy torrent that crashes against the mountains before spilling out onto a wide, flat basin. In 256 BC, that geography created a predictable cycle of disaster. When the mountain snows melted in the summer, millions of gallons of water surged downstream, drowning the lower plains in catastrophic floods. Then the seasons would flip. Winter brought severe droughts, completely paralyzing agriculture in the Chengdu Basin. Building massive, static dams to block this kind of energy rarely works for long. The sheer kinetic force of the floodwaters easily smashes through rigid barriers. You cannot permanently solve extreme fluid dynamics with brute force. Static walls inevitably break under the pressure of a shifting, living river. The Qin state appointed a local governor named Li Bing to permanently tame the Min River. Li Bing realized that trying to trap the water was a mistake. His solution relied entirely on redirecting the river's existing kinetic energy instead of trying to stop it. By shifting the engineering goal from conquering the water to guiding its momentum, he designed an infrastructure system that runs autonomously. This image shows the first major component of that system, called Yusui, or the fish-mouth levee. Its exact physical shape is designed to split the rushing river directly in two. Because standard dams would wash away, the builders used a different method. They packed heavy river stones into long bamboo cages, called zulong, and anchored them using heavy wooden tripods known as macha. This diagram illustrates the 4-6 divide. During dry springs, gravity funnels 60% of water into the deeper inner river for irrigation. When summer floods arrive, the excess volume spills into the wider outer river, automatically diverting 60% safely away from the plains. The precise topographical shape of the riverbed functions as a mechanical sensor. It continually adapts the water volume based on seasonal inputs, operating perfectly without a single moving part. Controlling the water volume solves only half the problem. Rivers carry millions of tons of heavy sediment and silt, which will quickly choke and destroy any standard irrigation network. To manage this, the builders constructed a second component downstream called Feishayan, or the flying sand weir. They positioned it at a specific curve in the channel to weaponize the river's own kinetic energy. As the river bends, intense centrifugal force pushes the heaviest, densest particles toward the outside edge. That outward kinetic energy lifts gravel and sand, autonomously flushing 90% of the sediment over the low weir, keeping the inner channel clean. The final obstacle was geographic. The solid rock of Mount Yulei completely blocked the purified water from reaching the plains. Centuries before the invention of gunpowder, laborers used thermal shock to cut through the mountain. They built massive bonfires against the rock face, then rapidly doused the heated stone with freezing snowmelt, causing the rock to crack and fracture. This slow thermal excavation eventually carved out the Baoping Kao, or bottleneck channel. It provided a permanent, perfectly sized opening to meter the exact volume of water flowing into the plains. Combining the centrifugal filtration of the weir with the precise rock-cut bottleneck yielded a perpetual, self-cleaning water delivery engine. The immediate historical result of this engineering was the creation of the Land of Abundance. Dujiangyan stabilized agriculture, generating the immense food surpluses the Qin dynasty used to unify China. 2,200 years later, this exact same system is still running flawlessly. Today, it irrigates 668,700 hectares of farmland and supports the water needs of over 50 modern cities. We can measure its structural resilience by looking at the 2008 Wenchuan earthquake. While magnitude 8.0 tremors shattered the modern concrete buildings in the surrounding cities, the ancient Dujiangyan infrastructure survived completely intact. Modern concrete dams, by their rigid nature, eventually disrupt fish migrations, degrade local ecosystems, and slowly choke on trapped silt until they require massive mechanical intervention. Dynamic systems that leverage natural fluid dynamics and integrate with local ecosystems consistently outlast and outperform rigid fortresses built to fight those exact same forces. The physical distance between Beijing and Shanghai is 1,318 kilometers. Traveling between them used to require an overnight train or a convoluted flight. Today, you can make the entire journey on land in just 4 hours. This map shows the connection between the Bohai Economic Rim in the north and the Yangtze River Delta in the south. Together, these two regions generate over 1/3 of China's total GDP. Connecting them required a $32 billion infrastructure project. The legacy conventional railways between these cities were entirely saturated with heavy freight and slow passenger traffic. Instead of attempting to upgrade that congested network, planners built a completely independent passenger-dedicated line. The objective was a continuous operating speed of 350 kilometers per hour. At that velocity, a train carries immense kinetic energy. Any sudden change in track geometry, a sharp turn, or a dip in the earth would result in catastrophic derailment or severe G-forces on the passengers. This visualization demonstrates the extreme geometric tolerances required to prevent centrifugal disruption. The track must adhere to a maximum vertical gradient of just 2. The ultimate manifestation of this viaduct-centric design is located near Shanghai, spanning a complex network of lakes, canals, and rice paddies. It is called the Danyang-Kunshan Grand Bridge. Measuring 164.8 kilometers, it is the longest bridge in human history. Building it required 10,000 people and a highly industrialized methodology, mass-producing standard-span, pre-stressed concrete box girders in casting yards and locking them into place at a rapid, continuous pace. This viaduct network functions as a continuous 1,000-kilometer structural foundation that entirely isolates the high-speed transit layer from the physical world below. The vehicles engineered to utilize this elevated track belong to the CR400 Fuxing series electric multiple unit. At 350 kilometers per hour, the primary obstacle is the atmosphere. Aerodynamic resistance accounts for over 90% of total drag forces. Engineers utilized extensive holographic simulations and physical wind tunnel testing to optimize the nose profile. The resulting shape reduced headcar drag by over 8% and mitigated the lateral shock waves created when two trains pass each other at full speed. Despite the violent aerodynamic forces battering the exterior, the interior environment remains quiet and stable enough to feature spacious business-class compartments and full-length dining cars. Propelling 1,000 passengers forward at 97 meters per second introduced a severe human biological limitation, one that aerodynamic hardware alone could not fix. At 97 meters per second, a human conductor's vision is physically incapable of processing mechanical trackside signals fast enough to safely react and brake. To solve this, engineers implemented the Chinese Train Control System Level 3, or CTCS-3. This digital control architecture entirely removes physical signals from the side of the tracks. This diagram illustrates the first technical layer of CTCS-3. Embedded track circuits continuously detect and report the exact physical location of every train on the line. That location data is instantly transmitted to a centralized hub known as a radio block center. The radio block center calculates a dynamic movement authority for each train. This is a precise mathematical allowance of distance and a strict speed profile that the vehicle is permitted to travel. This movement authority is beamed directly into the train's onboard computer interface via a dedicated GSM-R wireless network. This process is known as cab signaling. The system features an ultimate failsafe. If the train exceeds its approved speed profile, the automatic train protection system overrides the driver to force deceleration. Because it constantly calculates and enforces these safety margins in real time, the railway can compress the interval between trains operating at top speed down to a mere 3 minutes. CTCS3 functions as a digital nervous system. It converts a mechanical railway into an automated high-bandwidth data network, mathematically guaranteeing that the extreme volume and speed remain safe. Processing 3-minute arrivals requires massive urban terminals. This necessity led to the design of the Integrated Transport Hub, with Shanghai Hongqiao serving as the primary archetype for this model. Hongqiao is a dense, multimodal facility that fuses 30 high-speed rail platforms directly with an international airport, 5 metro lines, and regional bus terminals. Operating this scale of infrastructure requires a specialized logic known as incomplete cyclic scheduling. Rather than stopping every train at every station, this schedule prioritizes high-demand origin-destination pairs. It provides high-frequency, hourly express departures specifically for routes like Beijing to Shanghai. These non-stop express trains skip intermediate regional hubs entirely. With over 90 trains running the corridor daily, the express service completes the 1,300-kilometer journey in just over 4 hours. These megastations function as massive urban processor chips. They are engineered to ingest, route, and dispatch hundreds of thousands of humans across diverse transit networks. The result is a highly productive corridor that reliably carries over 200,000 passengers every single day. By combining centralized traffic control with AI-driven predictive maintenance, the operator yields an on-time performance rate of greater than 99%. High-speed rail captures over 70%. Shifting mass intercity travel from jet fuel to an electrified network creates significant economies of scale and massive carbon offsets. The Beijing-Shanghai high-speed railway proves that an uncompromising approach to track geometry, aerodynamic engineering, and digital signaling works at scale. It stands as the definitive global blueprint for the future of electrified, high-capacity mass transit. The Yangtze is the third longest river on Earth. Every second, immense volumes of water surge through the steep valleys of central China, carrying enough kinetic energy to carve mountains and, historically, flood entire provinces. This map shows the physical footprint of the precise barrier built to intercept that flow at Sandoping. The Three Gorges Dam is a concrete gravity structure 2,309 meters long and 181 meters high. Constructing it required pouring 27.2 million cubic meters of concrete. This mass holds back a reservoir with a total capacity of 39.3 billion cubic meters of water, raising the river level to create a maximum hydraulic head of 113 meters. The Three Gorges project operates as a highly calibrated dynamic hydraulic machine. It must solve 3 conflicting problems: intercept catastrophic flood surges, extract continuous clean energy, and maintain the busiest shipping lane. Balancing these massive forces simultaneously while managing a 113-meter vertical drop requires an intricate architecture of spillways, turbines, and mechanical lifts. This cross-section demonstrates the base physics of a concrete gravity dam. It resists the horizontal hydrostatic pressure of the reservoir almost entirely through the immense downward weight of its own concrete mass. This solid anchor allows the dam to execute its primary mandate, flood control. The reservoir maintains 22.15 billion cubic meters of capacity, specifically dedicated to absorbing excess water. This capacity was pushed to its limits during the 2020 Yangtze megaflood. Through careful dispatching, the reservoir absorbed the surge, physically intercepting 29.5 billion cubic meters of incoming floodwater. By holding back that volume, the dam regulated the downstream flow to a highly reduced 49,400 cubic meters per second, sparing downstream cities from inundation. Releasing that volume creates a severe fluid dynamics problem. Pouring water directly down a 113-meter drop will rapidly erode the bedrock foundation. To prevent this, engineers built a highly specific geometric array into the spillway section. They designed staggered, 3-layer large discharge orifices embedded directly through the main concrete body. This fluid dynamic simulation illustrates a technique known as ski jump energy dissipation. Rather than letting the water fall straight down, the curved spillways launch massive tongues of water outward. This spillway geometry transforms a catastrophic wave of kinetic energy into controlled fluid dynamics, ensuring the structure does not undermine its own foundation. While the spillways dissipate excess energy, the interior powerhouse is designed to exploit it. The facility houses a staggering array of generators, 32 main turbine units distributed across the left and right banks, plus 2 smaller plant units to power the facility itself. This schematic details a main Francis turbine. Measuring 9.7 meters across, these units are engineered for an 80.6-meter rated head. At maximum capacity, 991.8 cubic meters of water per second funnel through the penstock, slamming the turbine blades to drive the massive 80-pole rotor. This mechanical rotation is converted directly into electricity. Each of these main generators is capable of producing 700 megawatts of power. When all units are operating, the entire complex yields a total installed capacity of 22.5 gigawatts. Depending on seasonal precipitation, this highly calibrated array generates upwards of 100 terawatt-hours of electricity every single year. This output makes the facility the anchor of China's clean energy corridor along the Yangtze. By extracting the latent energy of that 113-meter drop, the station replaces the combustion of tens of millions of tons of coal annually. This brings us to the navigation paradox. The Yangtze is a critical economic artery. You cannot permanently sever the route, which means ships must somehow bypass a 113-meter vertical concrete wall. For heavy freight, the solution is a fully lined, double-lane, 5-stage ship lock. Operating as a massive water staircase, it steps 10,000-ton cargo fleets up or down in 20-meter increments, utilizing gigantic 855-ton herringbone gates to hold back the intense water pressure at each level. While it handles an immense volume of freight, it is slow. A single transit through the 5 locks takes approximately 4 hours. To complement this, engineers constructed a parallel, high-speed solution for smaller passenger and cargo vessels, a vertical ship lift. This lift is essentially an elevator for boats. It consists of a 120-meter by 18-meter water basin, suspended entirely in midair. Hoisted by 256 thick suspension ropes, massive counterweights and rack and pinion drives move a combined mass of 15,500 tons up the face of the dam. This split-screen comparison shows the time differential. While the heavy cargo fleet on the left requires 4 hours to clear the locks, the 3,000-ton passenger ship on the right completes the vertical transit in just 40 minutes. This dual-system bypass resolves the paradox of damming a trade route, perfectly separating slow, high-volume freight from rapid, low-volume transit. Yet controlling the water solves only part of the problem. The Yangtze River also carries a massive hidden geological threat. An average of 526 million tons of sediment arrives at the dam site every year. To counter this, operators use a hydrological strategy called storing clear and releasing muddy, flushing heavy sediment loads downstream during the flood season and retaining clear water in the dry season. Manipulating the river to this degree comes with severe environmental costs. The physical barrier has permanently interrupted natural fish migration paths between the upper and lower Yangtze. This separation has decimated local aquatic biodiversity, drastically reducing the endangered Chinese sturgeon population by cutting them off from their spawning grounds. Even with sediment flushing protocols, the reduction in downstream silt delivery has altered erosion patterns, causing riverbank instability along the lower reaches of the basin. Given these massive hydrological and geological pressures, the concrete body itself is under continuous extreme stress. To monitor structural integrity, the dam relies on a dense telemetry network. It utilizes vacuum laser alignments, GPS geodetic tracking, and internal piezometers to detect millimeter-scale foundation shifts. The megastructure remains an ongoing, highly managed compromise between structural physics, continuous environmental degradation, and constant safety monitoring. Looking at the Three Gorges project as a unified whole reveals a machine processing water, cargo, and electricity simultaneously across a single concrete axis. It represents a synthesis of civil, mechanical, and hydrological engineering executed on a geographic scale. By anchoring the flow of the Yangtze, it transformed a volatile river system into a highly regulated engine. It provides a vast baseline of continuous power to the national grid while facilitating one of the most vital supply chains on the planet. The Three Gorges Dam operates as a permanent, active machine, maintaining a perpetual balancing act between the raw force of nature and the demands of modern human infrastructure. Temperatures drop to -47 degrees Celsius. Winds exceed 30 meters per second. The Qinghai-Tibet Plateau is actively hostile to human infrastructure. Across this barren expanse runs the Qinghai-Tibet Railway. It is a 1,142-kilometer heavy rail line bridging central China to Lhasa. This chart displays the route's elevation profile. From Golmud, the track executes a relentless ascent, reaching its 5,072-meter apex at Tongula Pass. But beneath these peaks lies a greater hurdle. This bracketed section indicates 550 kilometers of track laid directly over continuous permafrost. Operating in this specific zone triggers 3 overlapping failures. The frozen ground is thermally unstable. The atmosphere thins out, dropping to 50% of the oxygen density at sea level. And the physical track threatens to isolate fragile migratory ecosystems. Standard heavy rail design relies on friction and mass, forces to generate enough heat to melt the very ice the track sits on. Yet, constructing an alternative is restricted by the atmosphere itself. There isn't enough oxygen to support the labor force required to build it. Standard civil engineering relies on passive, static resistance. Building the railway required abandoning that model entirely in favor of active thermodynamic and atmospheric modulation. The earth beneath the plateau is classified as warm, ice-rich permafrost. The soil profile is heavily laced with embedded ice strata, making it exceptionally sensitive to the slightest temperature fluctuations. In typical frozen environments, civil engineers rely on passive insulation. They build thick roadbeds meant to separate the infrastructure from the ground, acting as a static thermal barrier. A heavy train generates immense dynamic friction. Combine that mechanical heat with rising global temperatures, and static insulation simply gets overwhelmed. As the excess heat penetrates the permafrost, the subsurface ice melts. The ground loses its structural integrity, leading to a rapid subgrade settlement known as thaw collapse. Relying on traditional methods has a poor track record. Historically, over half of all railways built on permafrost have suffered frost damage ratios exceeding 30%. This chart displays the mean annual ground temperatures along the route. The shaded regions reveal temperatures hovering dangerously close to the 0 to -1 degree Celsius threshold. It is a razor-thin margin for error. To maintain the soil's shear strength, engineers could not just block the incoming heat. They had to build an infrastructure that actively extracts heat from the earth. The primary cooling solution is the crushed rock embankment. Instead of solid fill, engineers laid down loosely packed stones. In winter, the voids between the rocks allow convective cells to form. Cold, dense ambient air sink into the spaces, actively pushing warmer air up and out. This continuous circulation artificially lowers the permafrost temperature, freezing the subgrade solid far deeper than it would naturally. In summer, the physics reverse. Warm air is less dense and naturally stays near the top. Convection stops, and the rock layer transitions into a highly effective static insulator, trapping the cold beneath it. For highly sensitive sections where rock beds aren't enough, engineers installed a secondary thermal regulation system, thermosiphons, or heat pipes. These hollow tubes contain liquid ammonia at their base. The ammonia absorbs heat from the ground, vaporizes, and rises to the top of the tube, where finned radiators dissipate the energy. As it cools, the ammonia condenses and falls back down. It creates a continuous, passive thermal pump. It requires zero electricity, steadily rejecting geothermal heat into the freezing winter atmosphere. This system was deployed across the entire 550-kilometer permafrost zone. The railway does not sit on the permafrost. It functions as a massive, continuous thermodynamic machine designed to permanently alter the ground's thermal state. In areas where active embankments were insufficient, engineers opted for dry bridges, elevated tracks built over completely flat, dry land. The Qinghai River Bridge is the largest of these, spanning 11.7 kilometers. Driving deep pile foundations isolates the thermal mass and dynamic load of the train. It completely decouples the heavy infrastructure from the fragile permafrost below. Elevating the track also resolves the secondary constraint. The plateau ecosystem relies on unobstructed migratory routes, which a surface-level rail line would sever. The dry bridges function as 33 dedicated wildlife underpasses, allowing critical species like the Tibetan antelope to cross the railway's path without interference. The train bridge system acts as a unified architectural solution, resolving thermodynamic instability and preventing ecological isolation. Moving from the ground infrastructure to the interior of the passenger cars introduces the final variable, the atmospheric constraint at 5,000 meters. At this altitude, ambient atmospheric pressure drops significantly. Passengers are exposed to only 50 to 60% of the oxygen available at sea level. Fully sealing the train cars to act as aerospace pressure vessels was technically unfeasible for a standard rail operation, requiring frequent stops and car coupling. This schematic illustrates the Hybrid Oxygen Supply System, or OSS. Instead of fully pressurizing the cabin, the system monitors and regulates the exact partial pressures of oxygen and carbon dioxide. The first component is the diffusion system. It pumps oxygen directly through the HVAC, raising the ambient cabin oxygen to approximately 23.5%. The second component is the distributed system. For passengers suffering acute altitude sickness, individual ports provide highly concentrated oxygen directly at their seats. Generating this level of oxygen continuously places an extreme energy burden on the train. The OSS consumes up to 5 times the energy of a standard air conditioning system. These cars are high-energy life support systems. Every carriage is a dynamically sealed vessel, balancing atmospheric pressure and oxygen levels to sustain human life across the plateau. All of these systems converge in the operation of the GE NJ2 locomotives, pulling pressurized cars through the thin atmosphere. They achieve an operational speed of 100 kilometers per hour directly over continuous permafrost, a world record for this specific environment. The harsh conditions dictate that human staffing is minimized. 38 unstaffed stations are continually monitored via a centralized remote control system. Despite the dynamic mechanical loads and accelerating global warming, the subgrade damage ratio along the line remains at less than 1%. It is a megaproject that successfully integrates geotechnical thermodynamics, ecological permeability, and aerospace-grade atmospheric engineering. The Qinghai-Tibet Railway demonstrates that infrastructure survives extreme environments through precise, active thermodynamic adaptation rather than static resistance. Building in a vertical environment requires solving a problem of gravity, but building inside a porous rock wall requires solving a problem of geology. This is Tianmen Mountain. It's a pure carbonate limestone pillar formed 380 million years ago, eventually reaching a peak elevation of 1,518 meters above sea level. Near the summit sits the region's defining topographical anomaly, Tianmen Cave, a 131.5-meter tall natural void carved completely through the rock by millennia of water erosion. Maintaining access for millions of annual visitors creates a direct conflict between human demand and geology. The terrain consists of sheer drops and unpredictable crumbling limestone that cannot support traditional developments. Pure carbonate geology is too fragile to support the heavy-duty surface roads required for mass transit. Solving this required a suite of infrastructure designed to function where standard ground-based equipment cannot. For decades, the primary surface-level solution to reaching the cave was a punishing 999-step stone stairway. Physical climbs create severe logistical bottlenecks. Modern peak operations demand moving 7,000 people per hour, a volume completely impossible to manage safely on foot. The engineering mandate was highly restrictive. democratize vertical access to the summit without fracturing the delicate karst rock or scarring the mountain's natural silhouette. This 3D wireframe models the solution. Stripping away surface vegetation reveals a trimodal network, an aerial cableway, an internal tunnel, and a peripheral walkway. These intersect at specific transfer nodes, creating a continuous logistical loop to the 1,518-meter summit. By pushing heavy mechanical mobility completely off the surface, routing it into the air and deep underground, the design circumvents the fragile surface ecology entirely. The primary logistical tether is the Tianmao Mountain Cableway, built by French manufacturer Poma, connecting Zhangjiajie's urban core directly to the peak. It spans a total horizontal distance of 7,455 meters and achieves a massive elevation gain of 1,279 meters. Running continuously at 6 meters per second, the system maintains a throughput capacity of 1,000 passengers every hour. This vector graphic illustrates the mechanical challenge. A standard area lift operates below 25 degrees, but Tianmao's verticality forces an unusual 38.6-degree climb. At this steep angle, the heavy steel track cable requires immense tensioning forces to prevent sagging and maintain structural stability. Operating heavy aerial transport over inaccessible karst terrain necessitates rigorous disaster mitigation frameworks. Out of the 57 support stands anchored along the route, engineers designed 3 specifically for specialized emergency rescue operations. If a total mechanical failure occurs, responders execute a vertical rescue. They use the heavy track cable as a primary anchor point, individually lowering stranded passengers to the ground using evacuation harnesses. This protocol ensures extraction is possible, even against the fierce atmospheric winds whipping across the exposed rock face. The aerial ropeway bypasses the geological instability of the lower slopes entirely, effectively turning empty vertical space into a high-capacity mass transit corridor. Inside the mountain massif itself lies a more complex geotechnical solution, the Canny subterranean escalator system. This required carving a 12-segment, 897-meter-long tunnel system that climbs 340 meters straight through solid rock. This X-ray reveals the hazards of pure carbonate karst, riddled with hidden water channels and unstable limestone pockets. To prevent tunnel flooding, engineers mapped these hazards. Excavation relied on precise drill and blast methods, immediately applying shotcrete and steel mesh to stabilize the crumbling walls. Once the tunnel was secured, teams faced the mechanical challenge of installing and operating precision escalator machinery in a tight, unrefined, and highly humid environment. This diagram compares escalator geometry. Standard escalators tilt at 30 degrees. The mountain's internal 40-degree incline causes standard motors and brakes to hit thermal overload. Engineers developed specialized drive motors and heavy-duty braking systems capable of surviving this extreme slope without overheating. Installing them presented a logistical puzzle. The multi-ton escalator assemblies had to be redesigned into smaller, modular units just to physically fit through the narrow, unfinished tunnel entrances. By mastering the unpredictable karst interior, engineers created a system capable of moving up to 6,000 people per hour completely out of sight. On the mountain's exterior periphery, a network of cantilevered cliff walks manages pedestrian circulation at 1,430 meters above sea level. The spatial constraints here are severe. The walking surface spans merely 1.5 to 2 meters wide, suspended over drops plummeting up to 355 meters. This cross-section shows walkways supporting massive loads. Horizontal steel beams are inserted into the vertical limestone face. Workers drilled sockets, encasing steel supports in high-strength concrete. Flat concrete and glass panels are laid across, distributing the weight of daily pedestrians back into the mountain core. This modern structural engineering is a direct evolution of an ancient precedent, the Chinese Zandao plank road technique. These modern Zandao paths served a crucial dual purpose. Before carrying tourists, they acted as logistical arteries to transport materials for the subterranean escalator construction. Heavy machinery and helicopters simply could not access these cliff faces. The staging and assembly had to be done entirely by hand. Approximately 285 metric tons of escalator components were hauled manually via drum hoists along 200 meters of temporary, precarious cliff paths. It is a striking convergence, high-end structural engineering executed through ancient, labor-intensive installation techniques to conquer a vertical barrier that machines could not reach. To understand the value of this integrated system, we must look at the traditional surface alternative, the famed 99-bend heaven-linking avenue. While this 10.77-kilometer roadway is visually iconic, it is functionally obsolete as a primary mass transit solution for extreme topographies. Heavy surface roads in nature reserves create high localized exhaust emissions, require extensive physical scarring of the landscape, and suffer from unavoidable vehicle capacity bottlenecks. The tri-modal network solves this. By shifting the bulk of passenger transit to the subterranean escalators and aerial cableway, it effectively eliminates the need for high-emission shuttle buses on the upper mountain. Unlike the heavy concrete switchbacks that permanently cut into the geology, the subterranean transit network remains completely invisible from the outside. Pushing the infrastructure underground protects existing wildlife corridors and maintains the mountain's natural, unbroken silhouette. This philosophy of integrating structure with topography extends to the urban base, seen here in the 72 Qilu architectural complex. The Tiangong Qilu building features a 38-meter hollow central gate designed to align perfectly with Tianmen Cave across the valley. It creates a dual-eye vista, bridging modern architectural achievement directly with the ancient geological formation. Engineering in these extreme environments focuses heavily on aligning mechanical systems directly with existing geological constraints. Tianmen Mountain establishes a new global benchmark for civil engineering, proving that extreme geological constraints are no longer barriers to mobility, but invitations to build invisible, landscape-adapted infrastructure. China's natural river systems are incredibly powerful, carving massive trenches through the landscape as they push heavy, muddy water eastward toward the sea. But those east-flowing rivers created a severe geographic disconnect for the ancient state. The heavily militarized political capitals sat in the arid north, isolated from the fertile agricultural breadbasket in the south. Survival required an artificial, vertical river to connect these horizontal waterways. The solution was the Grand Canal. Stretching nearly 1,800 kilometers, the canal links 5 major natural river basins across the eastern plains. Centuries of hydraulic breakthroughs transformed a simple trench in the soil into a highly calibrated water machine. The early canal system was lethal. Engineers used primitive flash locks and double slipways to move boats between elevations, but the rushing torrents routinely shattered the wooden hulls of cargo ships. In 983 AD, a Song dynasty official named Cao Wei-yu engineered a solution to tame the rushing water, the pound lock. This diagram shows the mechanics of the pound lock in action. A barge floats into a walled chamber. The gates at both ends are sealed shut, and the water level inside is artificially raised or lowered to match the terrain ahead. Instead of fighting against a dangerous torrent, massive wooden ships could sit safely in a protected pool as they were lifted into the foothills. By utilizing the pound lock, human engineering proved it could force thousands of tons of cargo safely over uneven terrain. The ultimate geographic obstacle lay in the Shandong foothills. At 42 meters above sea level, water naturally drained away from the channel, leaving the canal dry. Engineers faced a massive logistical puzzle. They had to supply a continuous flow of water to the absolute highest point of a vast transit corridor. In 1411 AD, Ming Dynasty planners finalized their solution. They constructed the Nanwang Water Diversion Hub, a complex array of dams and sluices known as the backbone of the canal. Looking at a schematic of the hub, we can see the precise math at work. The incoming Wen River hits the dam and is split exactly. 70% of the flow is pushed toward the northern capital, and 30% goes south. Engineers combined this precise split with a stepped energy dissipation system. By spacing the locks strategically, they controlled the speed of the descending water, stopping the banks from eroding and maintaining navigable depths. By precisely taming the slope, engineers established the hydraulic heartbeat that sustained the northern capital despite its distance from the southern harvest. This entire 1,700-kilometer water machine existed for one primary output, the Kaoyun or tribute grain system. The state operated the canal as a strict imperial monopoly. It provided a protected inland supply chain completely insulated from the unpredictable storms and pirates of the open ocean. At its peak, the machine safely moved 400,000 tons of grain annually to feed the armies and bureaucrats stationed in the north. Maintaining this flow required an army of tax captains, navigators, and laborers, making it the most extensive civil engineering operation prior to the Industrial Revolution. The system effectively fused the northern military apparatus with the southern agricultural economy, binding the empire into a single political economic entity. Many ancient civilizations left behind grand stone monuments that now sit empty as tourist attractions. The Grand Canal never stopped working. Today, the waterway maintains its original purpose, handling hundreds of millions of tons of bulk cargo every year. The ancient hydraulic routing has been integrated into China's modern south-to-north water diversion project, earning its status as a UNESCO World Heritage Site in 2014. The exact hydraulic logic established by Song and Ming dynasty engineers still dictates how water and resources flow across the country today. With enough patience and precise engineering, the ancient designers successfully rewrote the geography of a continent to sustain a civilization for millennia. Traditional high-speed rail systems encounter a physical wall at around 350 kilometers per hour. At these velocities, the mechanical friction between steel wheels and tracks leads to extreme wear, limiting how much faster a wheeled train can safely go. Pushing the speed envelope further requires a departure from mechanical tracks, moving away from contact entirely. The starting point for this transition is the Shanghai Pudong International Airport, home to the world's first commercial high-speed maglev. This is the Transrapid. Even while sitting perfectly still at the gate, this vehicle is already flying. Exceeding the 350 km/h barrier isn't about perfecting the wheel, it's about mastering controlled electromagnetic flight. The Shanghai system uses electromagnetic suspension, or EMS. Instead of sitting on top of the track, the train's undercarriage wraps around the T-shaped guideway. This cross-section shows the hover mechanics. Electromagnets on the train attract to stators on the guideway, generating lift. To prevent physical contact, a control system samples the distance 100,000 times per second, maintaining a precise 10 mm air gap. Maintaining that microscopic 10 mm tolerance is an immense challenge in Shanghai, where the soft alluvial soil is prone to shifting. To prevent any movement that could disrupt the hover, engineers use deep pile-driven columns to anchor the guideway, ensuring the track remains perfectly immobile. The frictionless glide depends on this structural rigidity, a massive reinforced foundation specifically designed to preserve a 10 mm gap at 400 km/h. As the train departs Pudong, it enters a rapid acceleration phase. Within minutes, it reaches 431 km/h without a mechanical transmission or conventional wheels. To achieve this without heavy onboard engines, the system uses a long-stator linear synchronous motor, or LS-LSM. Think of the LS-LSM as a rotary motor unrolled and laid flat along the guideway. Its track windings generate a high-speed traveling magnetic wave. The train's underside magnets lock onto this wave, using simultaneous attraction and repulsion to pull the hovering vehicle forward. Because the propulsion hardware is built into the track rather than the train, the vehicle is stripped of heavy engine components, drastically lowering its weight. At the top speed of 431 km/h, the ride is exceptionally smooth. There is no rail vibration or mechanical noise, only the sound of the wind rushing past the hull. With the track handling both lift and propulsion, the train itself is reduced to an ultra-lightweight aerodynamic cabin. During this high-speed glide, mechanical friction is effectively zero. What passengers are experiencing is low-altitude flight, which alters the energy efficiency equation for high-speed transit by focusing power on overcoming air resistance alone. The train eventually begins its deceleration, entering a computer-controlled approach into the Longyang Road terminus in the heart of the city. The journey covers 30.5 kilometers in just 8 minutes. While the upfront construction cost was high, at over $1.3 billion, the system is designed for a different kind of long-term operational economy. Because the train and track never touch, the mechanical wear and tear that defines traditional rail is virtually non-existent. By eliminating physical contact, the maglev system significantly reduces the maintenance hours and part replacements required over decades of continuous high-speed service. The Shanghai line has proven its reliability over 20 years of operation, maintaining a punctuality rate of over 99.8%. This project served as the global proof of concept for the Transrapid technology, transitioning magnetic levitation from a laboratory experiment to a commercial success. That success has driven China's development of new systems, including the domestic S1 line in Beijing. The engineering foundations established here are now being applied to the next generation of 600 km/h intercity maglev projects. The Shanghai maglev demonstrated that the friction barrier isn't just a limit to be managed, but one that can be entirely removed, paving the way for a future of contactless transport. Modern aviation has a horizontal expansion problem. As passenger demand grows, airports tend to stretch endlessly outward, turning terminals into massive, unnavigable labyrinths. For the passenger, this sprawl creates a miserable experience. Mile-long walks between connections and a total reliance on disjointed shuttle trains just to move between terminals. By 2012, this limit was reached in the Jing-Jin-Ji region. The boom in northern China had pushed Beijing Capital International Airport to absolute breaking point. To maintain the region's growth, China needed a new regional megahub, one capable of eventually handling 100 million passengers and 4 million tons of cargo every year. But this created a difficult architectural paradox. How do you construct a 700,000 square meter terminal that feels legible and efficient, rather than overwhelming to the people using it? Beijing Daxing International Airport was designed by Zaha Hadid Architects and ADP Engineering to replace the century-old Nanyang Airport under a coordinated two airports in one city strategy. The core spatial logic is a reinterpretation of traditional Chinese architecture, specifically the principle of consolidating all interconnected spaces around a single central courtyard. By using this radial starfish layout, the design brings all primary services, security, check-in, and retail, into one compact building, completely eliminating the need for automated interterminal shuttle trains. This map shows the layout success. From the core, travelers reach the furthest of 79 gates in an 8-minute, 600-meter walk. By wrapping gates around this core, Daxing turns massive size into an advantage, prioritizing human movement. Looking upward, the entire facility is enclosed by a hyperboloid steel roof covering 350,000 square meters. The engineering density is staggering. To create this continuous, flowing canopy, the structure required more than 170,000 individual steel components. To achieve a column-free interior, the roof is supported by flowing C-pillars that funnel light to the floor. Engineers optimized the plan with 10 C-pillars to maximize daylight and intuitively guide passengers through the Grand Hall. This geometry serves as an intuitive layer of wayfinding. The way the roof vaults fan out toward the boarding piers acts as a passive structural compass for the millions of travelers passing through. While the roof defines the terminal's identity, an 80,000 square meter ground transportation center is hidden deep underground. This subterranean level is a massive transit node, with 5 different railway lines running directly beneath the active passenger terminal. This includes the Beijing-Xiang'an Intercity Railway, where high-speed trains pass through the airport station at speeds up to 250 kilometers per hour. This creates a unique vibration environment. The mechanical force of these trains, paired with local earthquake risks, could easily compromise the terminal structure. The solution was the world's largest base-isolated structure. By using isolation trenches to decouple the massive terminal from the earth, the building absorbs tremors and rail vibrations. This vertical stacking layers regional rail into a global hub without compromising integrity. Daxing's innovation extends to its environmental footprint, integrating renewable energy through photovoltaics and geothermal heat pumps. Its water management system uses a network of wetlands and lakes to collect 2.8 million cubic meters of rainwater, cooling the local microclimate while preventing floods. Initially serving 45 million passengers, the plan is built for growth, hitting 72 million by 2025 and eventually reaching 100 million. Beijing Daxing proves that a massive footprint can remain legible. By utilizing vertical integration, it shows that even at this scale, infrastructure can be engineered to serve the human experience. For decades, the Huangpu River and the Yangtze Estuary served as the foundation of Shanghai's global shipping power. Look at this sand barge making its way across the river water, with the hazy Shanghai skyline in the distance. But these inland waterways hide a physical bottleneck. They are only 7 to 13 meters deep, and they suffer from constant silting that requires endless dredging. This diagram reveals the modern maritime conflict. An ultra-large megaship carrying 20,000 containers needs a draft, or underwater depth, of up to 17.5 meters. If it tries to navigate a 13-meter riverbed, it scrapes bottom. Shanghai's geography was a hard barrier to growth. If these megaships cannot dock here, they take their volume to deeper water competitors in the region. To solve the problem, engineers realized they had to leave the mainland entirely. They looked 32 kilometers offshore, straight into the open waters of the East Sea. As we can see on this coastal map, the target was the Kiku Archipelago in Hangzhou Bay, marked here by the red star. It was a remote cluster of disconnected rocky islands. Unlike the silting rivers, these outer islands possessed a natural advantage. The surrounding ocean water naturally drops well past the 15-meter depth requirement. Executing the plan required physical manipulation on a massive scale. Engineers had to fuse these disconnected rocks together into a single colossal engineered machine. From above, the 32.5-kilometer Qinghai Bridge connects the artificial port to the mainland. Building over the open ocean demands extreme tolerances. Its concrete and steel are engineered to survive magnitude 7 earthquakes and resist marine corrosion for a century. Notice how the bridge follows a distinct S shape. This diagram illustrates why. The shape aligns the support pillars with the ocean's natural tidal currents, reducing head-on water resistance. It operates as a survival mechanism, holding a permanent, high-speed road over hostile deep water. Arriving at the Yangshan port site, you can see the contrast between the original rugged rocky hills and the geometric grid of the container yards. To create this terrain, crews dumped 100 million cubic meters of soil, expanding the islands and bridging the open water between them. But underneath that new land lay an invisible geotechnical threat. The ocean floor here consists of soft sea clay, which cannot safely bear the weight of millions of tons of stacked steel containers. To solve this, engineers utilized two-point vibroflotation. Mechanical probes vibrate violently, driving deep into the soft sea clay to compact it into a solid foundation. This geographic manipulation produced the solid anchor necessary to support the heaviest logistics operations on the planet. In the twilight, the automated terminal lights up the coast with illuminated red cranes and dense container stacks. But look closely at the ground level. 0 human operators are physically present on the terminal floor. Instead, a choreography of driverless machines takes over. 130 automated guided vehicles and 26 bridge cranes execute a synchronized ballet. An invisible digital brain orchestrates every movement. The terminal operation system and the equipment control system communicate constantly to route traffic, assign lifts, and monitor equipment health. This entire ecosystem, from the complex routing algorithms to the massive physical machinery, was engineered and manufactured entirely within China. By removing human physical presence from the dock floor, the port enables consistent operations that reach more than double the productivity of traditional terminals. This satellite view reveals a major threat for an offshore machine: severe marine weather, like the massive spiral arms of Typhoon Mufa. Instead of fighting the storm, the port calculates it. Artificial intelligence systems constantly measure wave frequencies and wind speed, sending micro-adjustments to stabilize the heavy cranes in real time. The human workforce is removed from the danger zone. Operators sit in downtown Shanghai offices, controlling the machinery over a 5G network, with the same ease they would use to win a stuffed toy from an arcade claw machine. This map shows the spatial disconnect in action. A remote operator's console in a mainland skyscraper sends commands over a 5G signal to an automated crane working 100 kilometers away on the offshore island. Remote automation allows the port to maintain high operational continuity while insulating the human workforce from the brute force of the ocean. Taking a wide aerial look, the Yangming container ship glides toward the automated red cranes, assisted by tugboats. The entire port acts as a single optimized organism, monitored constantly by a digital twin running predictive simulations. Operating at this scale, this offshore machine processes around 25 million standard containers every single year. That volume has cemented Shanghai's status as the world's leading container port for 16 consecutive years. Yangshan proves that when geography sets a hard limit on development, massive-scale civil engineering and digital automation can move a city's economic frontier 30 kilometers into the sea. Southwestern China's Guizhou province is a labyrinth of vertical limestone peaks and deep valleys. Over 90% of the province consists of extreme mountainous terrain. For centuries, this geography has acted as a natural fortress. It isolated local communities, cutting them off from coastal trade networks and keeping the regional economy disconnected from the rest of the country. When engineers pushed the G56 expressway across the nation to solve this connectivity problem, they collided with a massive physical wall, the Baihetan River Gorge. To cross this gap, drivers endured a grueling 4-hour detour down a narrow series of treacherous mountain switchbacks, constantly threatened by fog and rockfalls. Completing the national highway grid required bridging a 720-meter chasm. Doing so would compress a dangerous 4-hour journey into a seamless 1-minute crossing. Spanning a canyon of this size is difficult anywhere, but the cliffs here are composed of karst limestone. Over millions of years, water dissolves karst rock. The resulting stone is highly porous, brittle, and riddled with hidden caverns. Sinking heavy bridge foundations into the lower canyon wall will crack the brittle rock, punching through the roof of a hidden cave. Add to this the fact that the region is prone to magnitude 6.5 earthquakes, and total ground stability becomes a strict requirement. How do you permanently anchor a 20,000-ton steel megastructure into a hollow, crumbling mountain? The completed Dujiangyan Bridge suspends its road deck exactly 565 meters above the river. This altitude secured a world record, but engineers didn't push the bridge this high for the accolade. The elevation was a strict geographic mandate. To escape the fractured rock near the valley floor, engineers continually repositioned the bridge's alignment, scanning higher up the cliff face. At 565 meters, they finally located dense, competent rock, the only layer thick enough to hold the towers. But anchoring the towers is only half the battle. A deep canyon usually calls for a suspension bridge, but that design was immediately ruled out. Suspension bridges require massive subterranean anchors built into the banks to handle the extreme outward pull of the main cables. Applying that much outward tension would rip the anchors right out of the brittle karst cliffs. Instead, the team used a cable-stayed design. A cable-stayed system is self-balancing. The short side spans act as counterweights to the long main span. Instead of pulling outward against the mountain, the cables drive the immense weight of the deck straight down the towers as compressive force, right into the secure footings. The extreme altitude and the cable-stayed geometry are direct structural translations of the mountain's geological weaknesses. By moving the bridge up to 565 meters, the team solved the rock problem. But at that altitude, turbulent canyon crosswinds become an existential threat to the deck. Long-span bridges are highly vulnerable to vortex-induced vibrations. When wind hits a solid structure, it creates alternating low-pressure zones that can set off a harmonic resonance, literally shaking a bridge to pieces. To neutralize this, engineers abandoned the standard solid concrete box girder. Instead, they built the center deck out of an open steel truss. The open truss slashes the deck's mass and acts as a permeable sieve, allowing dangerous wind currents to pass harmlessly through. Additionally, the cables feature helical fillets. These spiral ridges channel rainwater away, preventing dangerous cable galloping. Assembling this high-altitude puzzle presented severe logistical hurdles, requiring engineers to utilize high-pressure gravity pumps to force custom-mixed concrete 270 meters straight up into the air to build the towers. By utilizing a highly permeable, lightweight steel structure, the engineers effectively turned the deadly atmospheric conditions of the canyon into a non-issue. The vertical distance between the Dujiangyan Bridge and the Baihetan River is difficult to comprehend. The entire Willis Tower in Chicago could fit comfortably underneath the deck of the highest mast. The Dujiangyan Bridge securely holds the highest record, based entirely on the vertical distance from the driving surface down to the earth below. These engineering records reflect the specific voids they were built to cross. A wide, shallow valley produces the tallest structure. A narrow, bottomless gorge produces the highest deck. With the canyon bridged, the G56 expressway is now seamless. A historically isolated region is physically plugged into a massive national trade grid. Proving that brittle parsed canyons can be safely conquered laid the groundwork for future megaprojects. The techniques refined here directly enabled the construction of the 625-meter Huashang Grand Canyon Bridge, a 565-meter deck anchored into rock, a cable-stayed system driving force down, an open truss breathing through winds. The Dujiangyan Bridge is a monument to geographical problem-solving. When extreme, hostile terrain presents a China houses approximately 20% of the global population, but controls only 7% of the world's freshwater reserves. The tension peaks in the North China Plain, home to Beijing, Tianjin, and vital agricultural centers. Here, freshwater supply per capita drops below 400 cubic meters annually, a level categorized as absolute water scarcity. On the ground, this statistical deficit materializes as desiccated topsoil and failing crop yields. The agricultural sectors that feed the nation operate in an environment naturally devoid of the surface water required to sustain them. A permanent structural flaw in the continent's geography creates the scarcity, placing a hard physical limit on the region's economic and demographic capacity. At this scale of deficit, local water conservation reaches a point of diminishing returns. To sustain the North, the state had to physically bypass the constraints of natural geography. For decades, the North China Plain survived by mining its groundwater. Municipalities and farms systematically drained subterranean aquifers to keep the surface economy functioning. Continuous extraction created massive subterranean voids. As the water table plummeted, the land above began to compress, causing severe geological subsidence beneath major urban centers. The concept for a systemic intervention was first articulated in 1952 by Chairman Mao Zedong. He proposed a brute force solution to the geographic mismatch: borrow a massive volume of water from the humid south to quench the north. That proposal eventually materialized as the South to North Water Diversion Project, marking a transition from local water management toward continental macroengineering. The project targets a redirection of 44.8 billion cubic meters of freshwater annually, physically rerouting the natural flow of the nation's hydrology. The infrastructure strategy relies on three distinct arterial routes: the eastern, middle, and western. Together, they physically link the Yangtze, Yellow, Huaihai, and Haihai river basins into a single grid. This grid functions as an active, mechanical reengineering of the continent's hydrological limits. The eastern route utilizes existing infrastructure by forcing transfer water through the ancient Beijing-Hangzhou Grand Canal system, a network of lakes and diverted rivers originally built for imperial trade. However, this route faces a severe topographical barrier. The destination in the north sits at a higher elevation than the source water in the Yangtze River. The water must travel uphill. This elevation profile of the eastern route reveals a continuous sequence of topographical steps, forcing water to climb a 65-meter hydraulic head. To defeat gravity, engineers constructed 13 major pumping station clusters, placed precisely at the elevation steps. These are massive terrestrial installations. The Jiangdu Hydro project serves as the critical intake point, acting as the primary anchor for the entire eastern ascent. The physics required here are categorized as low lift, high flow. To maintain continuous volume against the gradient, the 34 individual stations are equipped with a combined 160 massive hydroelectric generators. They exert sheer kinetic power, continuously lifting thousands of tons of water vertically, forcing it into the next sequential channel. This creates a systems engineering trade-off known as the water-energy nexus. Moving this volume of water requires immense, uninterrupted electrical generation. The eastern route successfully forces water against the natural gradient of the Earth, but it pays for that victory through continuous, massive energy consumption. The middle route operates on a different logic. It is an entirely new 1,246-kilometer artificial conduit, stretching from central China directly to the capital megaregions of Beijing and Tianjin. The system begins here, at the Dujiangyan Reservoir on the Han River. This facility provides the vast storage capacity required, and its altitude provides the initial potential energy for the entire route. This elevation profile of the middle route shows a stark contrast. From the reservoir to Beijing, the topography allows for a continuous, unbroken downward slope. By utilizing this grade, the 1,246-kilometer route is entirely gravity-fed, requiring 0 active pumping stations. However, this gravity flow intersects a formidable geographic obstacle, the Yellow River. The transferred water is clean, meant for municipal drinking supplies. If it mixes with the heavy, sediment-rich Yellow River, the transfer is ruined. To prevent contamination, engineers designed a system to cross the river by going under it. They constructed massive inverted siphons and deep subterranean tunnels, passing the fresh water far beneath the muddy riverbed. Excavating these conduits required large-diameter, dual-shield tunnel boring machines, carving directly through the deep bedrock to create isolated concrete arteries. The middle route trades extreme upfront capital costs and heavy terrestrial manipulation to achieve an optimal operational state, a high-volume, energy-free, gravity-driven flow. The final phase of the project, the planned western route, shifts the geographical focus to the Qinghai-Tibetan Plateau. The elevation parameters here are extreme. The proposed infrastructure must operate between 3,000 and 5,000 meters above sea level. Operating at this altitude introduces severe engineering constraints. The terrain is deeply rugged, highly active with seismic faults, and subject to deep freezing conditions. These environmental hazards make the western route the most complex phase of the transfer, pushing its targeted completion to the year 2050. Macro engineering at a continental scale carries severe secondary effects. Rerouting hydrology generates immense friction in both the economy and the local populations. The financial burden of the physical infrastructure alone is immense. Official cost estimates range from $62 billion to over $79 billion US. In the donor basins of the South, the ecological costs required raising dam walls and clearing vast tracts of land to expand the storage capacity of the reservoirs. To make way for the middle route infrastructure, over 300,000 residents were classified as ecological migrants. They faced mandatory relocation, physically displaced by the rising waters required to sustain the distant northern cities. Operationally, the state faces an ongoing administrative dilemma, pricing the diverted water high enough to recover maintenance and pumping costs, but low enough that northern municipalities can actually afford to consume it. The true cost of altering a continent's hydrology extends far beyond the initial pour of concrete. It commits the state to perpetual social and ecological management. That the physical outcomes in the North China Plain demonstrate exactly why that price was paid. With the eastern and middle routes operational, the diverted water now sustains over 150 million people, supplying roughly 70% of the total drinking water for the capital megaregions of Beijing and Tianjin. This new supply triggered a critical replacement logic. By substituting imported river water for local groundwater, authorities were finally able to seal and shut down the deep agricultural and municipal wells. This line chart plots Beijing's groundwater depth over 10 years. In 2014, the water table plummeted to 25.7 meters. But following the completion of the middle route, the downward trend halts. By 2019, the water table had risen to 22.7 meters. Beneath the concrete of the city, a physical reversal is occurring. The dry, fractured aquifers that were drained for decades are slowly refilling and repressurizing with water imported from 1,000 kilometers away. The South-North Water Diversion Project establishes a reality for the 21st century. A region's hydrology is no longer strictly dictated by its local climate. It is defined by infrastructure capacity and the systems engineered to sustain it.